Hello Year 12. So today we're going to be looking at DC motors and how torque occurs in a DC motor. Now previously we talked about the different components of a DC motor, what's involved and all that. Today we're going to revise something that we did in module 5, which was about torque. So we're going to look at how is torque produced in a simple DC motor. Now, firstly, we need to revise what is torque. Torque is the amount of force during rotation of an object on its axes. It's a vector, so there is a direction. We define the basic formula for torque as tau equals to force times the axis of rotation. That force is perpendicular to our axis of rotation. In this diagram here, our axis of rotation is L, so that's what R is. Our force, if you can appreciate, is at 90 degrees to our radius at all points. When we refer to something as rotating, it is some form of circular motion, so it rotates around like that. If we switch the scenario around and we have torque that's being produced at an angle, so we apply a force, so this is our radius, and this is the force we apply onto it. In the diagram we have here, the force we apply is not 90 degrees, it's 60 degrees. So how do we solve it there? I already have the actual formula, but I'll show it to you step by step. So let's say we have a force vector down this way, and this is just based on something we did in module 2, where we try and resolve a force vector into its two perpendicular components. So I know that the perpendicular component of my force is this direction here. Okay, this is F perpendicular to the surface. Well, that's the assumption I'm going to make. This has our force vector, and we said that there are two perpendicular components to this force vector, which means not only do I have a line going up like this, I should also have another line that comes along this way across. And this should also be a 90 degrees angle, which means this line and this line up here are parallel to each other. In the question, we said that this angle is 60 degrees, and so 180 is the total sum of a triangle, minus 60 minus 90, we have a 30-degree triangle on this side, and then 60 degrees here. If I look at the relationship between F and F perpendicular, the function we get, or the trig function we get, is sine theta. So sine theta is equal to the opposite over hypotenuse. F perpendicular is the opposite side, and F is the hypotenuse side. If I move F over, so F times sine theta, I get F perpendicular. If I sub that into the formula, so tau equals to F perpendicular times the radius of rotation, then tau is equal to F sine theta r. And remember, this theta here is the relationship that the force you apply onto the rotating axes. So this rotation here. Moving along, these were the definitions, or these were the formulas we looked at in Module 5. So if you're not sure, refer back to Module 5. So this is from Module 5. And these were all what we said. So theta is the angle applied between the force and the arm, or you could say the rotation or the radius. Tau is torque. It's given in Newton meters. R is the perpendicular distance between the forces. F given in newtons because it's a force. Obviously, F with this little shape here refers to the perpendicular force that is applied onto the radius. If I try and collate that into what we did, so this is the formula we established from Module 5. In Module 6, we learnt that if you have a current wire, so we have a current carrying wire, and we expose that to external magnetic field, so let's say we have a north pole here, we have a south pole here. Right, a force will be applied onto our current carrier, and the force, the magnitude of that force, is equal to the current times the length of the wire exposed to the magnetic field. So if I want to work out what the length is, this section here is the length that is exposed. Horrible looking L there, I do apologize, but that's the length exposed in our magnetic field. Sine theta. Sine theta is just where our current carrying conductor is being exposed to the magnetic field. In this case, because it's just cutting straight across my B field, it is 90 degrees to the magnetic field. Let's assume in a motor things are slightly different. So instead of having a single wire, in a motor you generally see something like this. So you see a loop of coil instead of a straight wire. So we have a loop like that. If I then try and draw out my magnetic field again, the scenario is still exactly the same. So we have a north pole, we have a south pole, and our B field is just moving along the same direction. Okay, so instead of looking at the radius, let's look at the width of our Y loop. So this is the width here, and this little part here will be the length. So this will be L. Just change that. So the length of the Y coming across that's exposed to the magnetic field, that's our L. Okay? So this is the formula we have here. We simply replaced the R here with D as the width. L here is the length exposed, which is this bit here. We know that area of a rectangle or a square is the length times the width. So if I fuse these two together, we're saying that A is equal to the width times the length. If I sub that in together, I get this equation here. So tau is equal to the current, the area vector, times B. Where did sine theta go? Well, essentially sine theta, we're making the assumption that the area is perpendicular, so 90 degrees, so sine is equal to 1. So in this case we're saying sine 90 is equal to 1, so we don't include that into our equation. What does A perpendicular really look like? Well, the area vector is essentially 90 degrees to the plane of my coil. So this is the plane of my coil. If I try and draw it so that I'm looking at it on the side, so my little eyeball here, if I'm trying to look at it on the side, this is the plane of my coil. This is my area vector A. So vector A is always acting at 90 degrees to the plane of the coil. So this bit here is the plane of the coil. And the area vector is always acting at 90 degrees to it. That's essentially what this formula means. So if I have a loop of coil, the only thing that is required to cause some kind of rotation, so to cause it to rotate, you need to have it at some kind of fixed area. It doesn't really matter what area it is, but it just needs to have some kind of area. You need current in the wires, that's a given, because without currents in the wire, you can't really get the motor effect going. And then B, you need a magnetic field. So north, south is what we have here. So three things to make a torque occur. So sine theta there, there's that. If you want to get maximum torque, then that means the area vector here, needs to be 90 degrees to the magnetic field. And I'll show you that in a second. Okay, so we talked about the area vector. So area vector, let's say it's coming out the page like this. So in dots coming out the page. Alright, another way of looking at it is like this. So this is the plane of the coil. So that's the plane of the coil. That's essentially what we're seeing on this side here. Now sine theta is what angle is created between A, the area vector, to the magnetic field B. So it's always going to be 90 degrees. The area vector is always 90 degrees to the plane of the coil. So we can disregard this part here. So the angle theta we're actually looking at is this bit here. So this is theta. So whenever you're looking at the angle you need to put into your calculation for torque, you need to do this part here. And that's what you're essentially trying to look into. That also means if you want to work out torque, you're looking at this component here. So we're assuming this is our 90 degrees, if we keep extending that. So this is the F perpendicular component we are looking for or searching for. Again, at the angle theta. So this is the component we can use to work out the amount of torque on this side and obviously the other side of the wire. These need to be in its relative components. Okay, that will tell me the torque or the rotation that's occurring with my motor. So these are the formulas that we have. It's essentially the exact same thing. The only extra thing I've added to the formula is N, and that's essentially the number of wires in the DC motor. So N is just the number of wires in our DC motor. Obviously, if it's just a number, there are no units, so that doesn't really matter. The reason why we have additional numbers of wires is More wires will increase the interaction between the current or the charged particles and the electric field. So that will increase F as well. So if I want to look at the force, it actually follows the exact same notation. If I increase the number of wires, there's greater force being applied onto the wire. So if I have greater amount of force, I'll also get a greater amount of rotation. So if you increase the amount of force you apply, or the force that's applied onto the wire, as a consequence, you should also see a greater amount of rotation in torque. So it's not torque that creates the amount of force, but if you increase force, you'll increase the amount of rotation moments that you get. Okay? And sine theta, or the angle theta, is in reference point the area vector A makes to our magnetic field. B is obviously in Tesla's magnetic strength, and current is obviously in amps. Another way of looking at it is using cos theta. So what's the difference if we have a look? If you're looking at maybe not black, maybe a different color, let's say blue. So this here, this is our area, area vector here. Okay? So this angle, if I just, instead of using theta, let's use phi. Okay? If I use this angle here, that's when I use this formula. So 𝑛𝐼𝐴 sine theta. And perhaps for some of you, you don't like to remember it in terms of where the area vector cuts the magnetic field line, and that's okay. Phi, sorry. And that's okay. Another way some people interpret the angles is the angle that the plane of the coil, so what angle does the plane of the coil make to the magnetic field? And so my plane of the coil is just this whole section here. What angle does this whole thing make to the magnetic field? And we can call this angle theta. Or if you don't want to confuse the two, you can call one phi and you can call one theta. And so if the plane of the coil is your reference point, you can use cos instead. Okay? So if you use cos, you're looking at the plane of the coil to the magnetic field. If you're using this angle here, it's the area vector to our magnetic field. And that's the main difference of if you use sine theta, if you use cos theta. So this one is if you used sine theta as a reference point. Just a little couple of questions for you to try. There are some more, but I will go over them in a bit more detail later on. Give yourselves about 5 seconds to pause this video. In 5 seconds I will move on and explain how these questions work, so you have been warned. Alright, so we are moving towards the answers. If you don't want to be spoiled, I suggest you pause it now. Alright, so here are the questions we've been given. A good starting point is to always highlight the quantities that's given to you or known to you. So we know that B is 0.1 Teslas. We know that theta is 45. We know that our area is essentially 20 times, and this needs to be converted into meters. Okay, so 20 centimeters squared, that is essentially saying the timesing of our area, so it should be 20 to the power of minus 4 meters squared. That's our area here. Okay, we need to square that across. The reason why we can get that is, if you recall, centimeters, or to make 100 centimeters equals to 1 meter. So you have that squared. To do that conversion from centimeters to meters, it's divided by 100. If it's now centimeters squared to a meter squared, then you have to do twice the amount that you had there, or sorry, the squared amount of that. So it would need to be divided by 10,000, which is where we get this number from. The torque we're already given, which is equal to 0.05, and then the current we're given, or the current is the thing we need to find. Okay, and so it's nicely laid out for you already what you need to do. So if I then put this into my formula, and do remember, in the HSC you are given marks for the correct substitution, so I strongly suggest you to substitute in the numbers before you try and rearrange any of the formulas. What you'll find is the answer is roughly, and this is just an approximation, it's roughly 353 amps, roughly around there. If you did do it in your calculator like I did, you'd actually find it's more closer to 353.55. So technically this number should be rounded off to 354 amps. And so you get that. Question 2. This time we're looking at the amount of torque being generated, and we also need to look at the direction of rotation. So let's see. We have side lengths of 5. So the area, if I convert that, is 5 times 10 to the minus 2. And I do that twice because it's square. So I get overall 25 10 to the minus 4 meters squared. The current is just 1 amps. The field strength is equal to 1 times 10 to the power of minus 4 Teslas. And then what else do we have? Do we have N? It's not given in the question, is it? So if N's not given in the question, it's safe to assume we're just dealing with one wire. Well, as you can see in the diagram here, which is our reference point, there is only one wire, so there you go. If I want to work out what theta is, I can see that my area vector is going directly up. So if I try and draw that as looking at from the side, this is the area vector coming along here, and this is what the magnetic field lines are doing. It's just going 90 degrees across the area vector, just 90 degrees across. So if sine 90 is 1, then we don't need sine theta in this case. Okay, so let me write that down as well. for those who didn't quite pick up what I said. So according to my graph, sine theta is 90 degrees, which is just equal to 1 in this case. If I forward it over, that's the working out we have there. Okay, so our current is this one here, and N is this one here for the number of turns. We have the B field, which is already written out here for you, and we have the area of the coil. And so that's the number you should get. Okay, so you should get 2.5 times 10 to the minus 7 Newton meters. Now I can do that just by checking myself off here, just to make sure that's the correct calculation given by my calculator. Okay, and so I have 1, 2, 3, 4, 5, 6, 7, minus 7. Sweet. The next bit is to work out the direction my coil is rotating in. So first thing is to work out where the current is going. So if you use your right hand rule, remember this is how it works. A really horrible looking right hand, but oh, that's actually my left hand, but let's redraw that. This is what happens. So we have our right hand here. Okay, your thumb is the direction of the current. Your fingers is the direction of the magnetic field, and the direction of the palm is where the force is going to be applied. Now, where the force is pointing, that's going to give us this idea of where the coil will rotate. So, if I look at the very first one, so on the left-hand side here, my current is going this way across. I can just make the assumption that it's going into the page. So using your right hand for lengths A, B, thumb goes into the page. My B field, my magnetic field, is pointing to the right. And so if you look at where your right hand is pointing, it's pointing down. So the force is coming down in this direction here. Let's look at C and D. Now C and D is coming in the opposite direction to A and B, so I can say my current is coming out the page, so I'm pointing out. My fingers are still pointing to the right because that's the direction of the magnetic field. And then looking at the direction of my palm, it's pointing upwards. So my palm is pointing upwards. This is the rotation. This is the rotation. This is torque. So it's going in a anti-clockwise direction. And that is the answer to question 2. Has a torque value of 2.5 times 10 to the minus 7 Newton meters, and it is rotating anti-clockwise. If you do have any other questions, let me know, and I will try and answer them in the comments.